Yes. So good evening one and all. So in mass spectrometry, in your last class we discussed about what is mass spectral pathways. Mass spectral pathways nothing but we are following some generalized rules. Based on that rules we are making some fragmentation. So generally if I take any odd electron ion, that will undergo fragmentation to give odd electron and even electron. So this odd electron also called radical cation, responsible to give radical cation plus a neutral. So this and this both are same. This is called odd electron rule. According to mass spectral pathways, if any odd electron ion undergo fragmentation, that will give one odd electron and even. Odd electron ion nothing but any ion carry odd number of electrons. Even electron ion nothing but any ion carry even number of electrons, 2, 4, 6 like that. Odd number and here even number. So if this ion undergo electronic impact, during electronic impact when electrons are colliding with this one like this, then this molecule or ion undergo fragmentation and that will give odd electron ion and even electron ion. This is called odd electron rule. Then what is even electron rule? Even electron rule. This rule is saying that when even electron ion is bombarded with electron, that will give even electron ion, and one more is even electron ion. Same. So the difference between odd electron rule and even electron rule is only type of ions. If it is odd electron ion, odd plus even. If it is even electron ion, both are even. So that is a key step involving in mass spectral pathways. Only these three particular reactions will decide the spectral fragmentation, whether it is exist or not. So we need to know whether that fragmentation is possible or not, right? See, in mass spectrometry we are not doing a random fragmentation. Whichever direction you want, you are not making any kind of fragmentation. We are following some rules. So what are the three rules for mass spectral fragmentation? First rule, if it is a odd electron, otherwise radical cation. Radical cation nothing but odd electron. So that will give radical plus cation. And what about one more? Radical cation will give radical cation plus a neutral. Then what about third rule? So this is even electron ion, nothing but cation. So even electron will give even electron plus even electron, also called cation, responsible to give cation plus neutral. So these three rules will decide whether given fragmentation is correct or wrong. In total mass spectrometry, if you are familiar with these three rules, so complete chapter will be in your hands. Only three particular rules. Okay, this is called odd electron ion. It is also odd electron ion. And what about this? Even electron ion. Okay, so in place of RC I can also write odd electron ion. Both are same. So yesterday completely I explained about what is odd electron ion and what is even electron ion, how they are undergoing fragmentation. Everything is cleared, right? Now see, now we are going to discuss what will be the fragmentation rules for a different functional groups and what are the key fragmentations are observed in a mass spectrometry. Okay, keep heading. Fragmentation rules. So what is the meaning of fragmentation rule? Remember the 3 points and we are applying for variable molecules. What are the common characteristic fragmentation and what are the functional groups responsible to give this fragmentation? That will be explained here. Okay, so first point, see, right, in straight chain alkane, you know alkane, single bonds, carbon single bond, nothing but alkane. In straight chain alkane, loss of CH2 unit. So what is MZ value of CH2? 14. MZ is 14. Every carbon 12, every hydrogen 1. So 12 plus 2 how much? 14. So in straight chain alkane, loss of CH2 is a characteristic fragmentation. You write clearly. So whenever if you want to do any fragmentation of alkane, if it is a straight chain, loss of CH2 will be takes place regularly. On the time, which rule we are following? Even electron rule. First is a odd electron, later on regularly even electron rule we are following. So when two adjacent peaks are get differ by 14 units, that molecule becomes an alkane in mass spectrometry. Suppose if any mass spectrometry is given for you, mass spectral data, 2 peaks are get differ by 14, 14 regularly, which belongs to alkane. Okay. Suppose one example I will show, you will understand clearly. See, here I am writing 5 carbons. When 5 carbons are present, I would like to make 70 electron volts electronic impact. Then it will form a molecular ion. So, this is a molecular ion of this molecule. This is cation and radical, and this is CH3. So between these two, 2 electrons are available. One of the electron I removed, then this becomes a cation. Loss of 1 electron. Now what is the MZ value of this molecule? MZ value. How much? So every carbon 12, every hydrogen 1. So 1, 2, 3, 4, 5. 5 into 12, 60. 65, 70, 72. So MZ value is how much? This is 72. Clear? First fragmentation, see here how many electrons are present? Only 1 electron. So is it an odd electron? Is it odd electron or not? Odd electron nothing but which may carry odd number of electrons in total molecule. Odd number of electrons in total molecule. Now what happens? See, try to remove this fragmentation. Hemi-heterolysis. On that time, what you'll expect? CH3, CH2, and here CH2, and here one more CH2 plus, and what is removed here? CH3 dot or not? Now, what about this? Is it an odd electron? It is an odd electron. And what is this? Even electron. See, when any odd electron undergo fragmentation, you will get odd plus even. Matching? Yes. Then later on, see, is it an even electron ion or not? Now, this will try to remove one CH2. So, if I remove CH2, what is the fragmentation? CH3, CH2, CH2. Now, this is an even electron ion. And what is one more? CH2. Then CH2 is also even electron. Following rule or not? Okay. Then one more time fragmentation. Remove CH2. If I remove CH2, what will get? CH3, CH2 plus. What is the difference between these two? 14. And if I remove one more CH2, then what is the answer? CH3 plus. Every time what is removing out? CH2. And here also what I removed? CH2. See. Even electron giving even electron, even electron. Even electron giving even electron, even electron. So what is the MZ value of this one? 57. MZ value is 57. So from here to here 15 difference. So after removal of CH3, regularly 14, 14 difference you will get. So then what is this? This is 43 and this is 29 and this is 15. So if you see the mass spectrometry of alkane, you will get like this. See here. This is MZ value. This is percentage of intensity. So what is molecular ion? This is molecular ion or not? Molecular ion is 72. Then what about next one? That is 57. So this is little bit intense. Then here this is intense peak. Then little low intense and this is low intense. So what about this? How much you expect? 72 minus 15. 57. This is 57. Then here 43 and this is 29 and this is 15, right? Now what is the difference between these two? 15. And what is the difference between these two? 14. And here difference is 14 and here difference is 14. See, if first difference is 15, later on remaining all are 14, 14 if you are getting, it is definitely a straight chain alkane. There is a code to identify. Suppose here how many carbons are present? 1, 2, 3, 4, 5 carbons are present. I may take 6 carbon, 7 carbon, 8 carbon, straight chain. Number of carbons are keep on increasing. Okay, every time then what is the difference? 14, 14 it will be difference. So, when molecular ion next peak get differ by 15. After 15 difference, regularly you will get 14, 14 which indicates that given molecule carry straight chain. There is no branched chain in that one. So based on this one can identify very easily what kind of connectivity present within the molecule. Whether it is alkane or not, we can identify very easily by using 14 difference. See, between these two 14 difference is there, 14, 14 and here 15. Here 15, 14, 14 indicates that the spectra belongs to alkane. Functional group is alkane. That is a strategy. Clear? How to identify alkane in mass spectrometry? How to identify alkane in mass spectrometry, straight chain alkane. First difference is 15. Next remaining all differences are 14, 14, 14. So if this kind of spectra appeared anywhere, you need to identify the differences every time. This is molecular ion minus 15, 57 minus 14, 43 minus 14, 29 minus 14, like that. If you compare every time, you will get some difference value. Based on this difference, first you can confirm what type of functional group it is. Clear? Right. So what is even electron rule? What is even electron rule? According to even electron rule, if any even electron ion undergo fragmentation, that will give two even electron species only. It may be a even electron ion and neutral. This is ion and this is a radical. We can say even electron ion, but this is not a odd electron ion. It is a odd electron species. Ion means either cation or anion. This is applicable only for straight chain alkane. If it is having no branches, all are straight chain. Pentane, hexane, heptane, octane, nonane, like that. Then two adjacent peaks are get separated by 14 units. Clear? So second point in that one. Suppose if I take any branched alkane, in branched alkane, fragmentation takes place at branched carbon. It will take place at branched carbon. Okay, so the outgoing radical, is long chain hydrocarbon. It should be a long chain hydrocarbon, means which carry more number of carbons and hydrogens. So here see, what is this indicates? These two carbons are bonded by two electrons. Right now one of the electron I removed. That's why written plus. So what is the use of the 70 electron volts which can remove one of the electron? Right? Here I remove one electron, that's why written positive. What is the meaning of positive? Loss of one electron. Negative nothing but gain of one electron. So between these two carbons, how many electrons are present right now? Only one electron, not two electrons. So when only one electron is shared between these two carbons, that's why it is called two-centered one electron bond. Two centers are there which is shared by one electron. So now this is applicable only for which one? Straight chain. Now what I am giving now? Branched chain. Otherwise you can say branched alkane. Now the thing is, this is alkane, this is called branched carbon. So when any branched alkane is given, loss of electron takes place from this carbon only, because this carbon having methyl, methyl, ethyl, everywhere branches will be there. So when 70 electron volts is applicable, then see, where should I remove? Already one point explained. In branched alkane, always try to remove electron closer to branched carbon. Remove from here. Don't remove this electron. So if I remove here, what should I write? Plus. And this is radical. And what about here? CH2 and one more is CH3. Clear? See, what is the statement? In branched alkane, fragmentation. This is called fragmentation. Here I want to make a fragmentation. Fragmentation takes place at branched carbon. Over here only fragmentation is possible. What is the meaning of fragmentation? Breaking. Breaking possible over here. So you may ask one more question, sir, why not above, why not left side, why not below? Everywhere branch is there or not? Because see, the outgoing radical is a long chain hydrocarbon. See, this carbon carry one more carbon or not? But this carbon carry only hydrogens. Here also hydrogens. Here also hydrogens. So always outgoing radical should carry more number of hydrocarbons. So if I break this one, what about here? CH3, CH3, and here this is CH3. And what about next? This one. This becomes a ethyl radical or not? CH3, CH2 dot. So which is outgoing radical? Hydrocarbon. How many carbons are present here? 2 carbons, 5 hydrogens. Suppose if I write hydrocarbon here, radical cation, I would like to remove CH3. Less number of carbons and hydrogens. So if any branch is given, always target the branched carbon having more number of substitutions. This is the target carbon. So this carbon carry 4 electrons inside. Try to remove that particular carbon electron which adjacent having more number of carbons and hydrogens. This side only I want to remove, fragment. Clear? So what is the MZ value of this one? Every cation, try to write MZ value. Don't write MZ value for radicals and negative ion. Try to write only for cations itself. MZ value of this one. 4 carbons are there. Every carbon 12. 1, 2, 3, 4. 4 into 12. 48. 51. 54. 57. So MZ value is 57. Then what about this one? How many carbons are there? See, last case how many carbons I taken? Last case how many carbons I taken? 5 carbons. Here how many? 1, 2, 3, 4, 5, 6. Like that you need to remember some selective values. If 5 carbons are there, what is MZ value of parent? 72. To that what I am adding? To that what I am adding? 14. Add 14 for that. 72 plus 14. How much? 86. Just calculate. Just calculate here. 1, 2, 3, 4, 5, 6. 6 into 12. 72. 72. Then 5. 77. 86. Very easy. If you know 12th table, mass spectrometry is easy. Okay. So what about MZ value? 86. Suppose if 7 carbons are there. Add hydrogens in that one every time. Add 14. 86 plus 14, that's it. 72, we are adding 14 or not? Then we are getting 86. Because this is a parent. Suppose if you want to do fragmentation, remove 14, 14, 14 every time. First is 15, remaining all are 14. This is applicable only for straight chain, but this is applicable for branched chain. Clear? Right. So is it a odd electron ion or even electron ion? This is odd electron ion. Odd electron ion give even electron, and what is this? Odd electron. One electron is present or not? Only one electron. If 3 electron, 1 electron is present, that is called odd electron species. But here, there is no independent electron. All are paired arrangement of electrons. So I can say it is a even electron ion. You follow the rules. That is the use of mass spectrometry. If you know the mass spectrometric pathways, fragmentation rules are very easy. So, this fragmentation is correct. According to the rule, this fragmentation is correct. Every time you need to remember like that. If any straight chain is there, loss of CH2 is a successive fragmentation. If any branched chain is there, outgoing radical is a particular carbon which carry more number of carbons and hydrogens. Hydrocarbon which carry more number of carbons and hydrogen is a outgoing radical. Next, third point, see. So, if I take any cycloalkane, in cycloalkane, loss of ethene, you know, ethene, alkene, loss of ethene is a characteristic fragmentation. It is a characteristic fragmentation for this one. So, what is the meaning of ethene? Alkene. Loss of alkene is a characteristic fragmentation. You know cycloalkane? This is cycloalkane. Suppose if I apply 70 electron volts, where should I remove electron? Can I remove from here? Here how many electrons are present? 2 electrons. Can I remove one of the electron? If I remove one electron, what do you expect? Here radical and what is this? Cation. Right? Between this carbon, any bond is present or not? Yes, bond is there. That is single electron bond. So don't think that there is no bond. Bond is there. Okay. So after getting this, see how to write a mass spectral fragmentation. See, you make a homolytic fission here. Homolytic fission. This radical forms double bond. And this radical cation forms a 4-membered ring. So can I write like this? Here this carbon forms double bond. Right? And see here 1, 2, 3, 4. 4 carbons are present. This is radical and what is this? Cation. So this can I write like this? Put a bond, write down radical cation. Right? Is it a odd electron ion? odd electron. What is this? Odd electron, and this is neutral, even electron. Following or not? See what I removed from any cycloalkane? If any cycloalkane is given, try to remove every time alkene. If you remove this one fragment is going to be appeared in mass spectrometry. Try to remove every time ethene. What is normal mass of ethene? Mass of this ethene 28. Every carbon 12, 12, 24, 26, 28. Here 2 hydrogens, here also 2 hydrogens. Slowly it can, you will get more clarity if you practice with more number of examples. But every time remember, try to prepare 12th table up to 10. If you know 12th table clearly, you can write MBZ value clearly. Otherwise, counting mistakes will be there. See, here this is 1 carbon, here 1 more carbon. 2 carbons are there or not? 12 into 2, 24. Here how many hydrogens are left here? 2. Here also 2. 24 plus 4, 28, over. But that is not MBZ. What is that? Mass. MBZ value you can write only for cations only. For this we can write. Can you calculate how many carbons, hydrogens are present here? What is MBZ value of this one? Count once. How much MBZ? Every carbon carry how many hydrogens? 2. Answer is 56. Right? So what is the difference between these two? Your MBZ value is how much? 56 or not? And what about MBZ value? Calculate fast. See what is the mass of this one? 28 or not? Add this 28 to this one. Because this I removed from this molecule. If you make sum of these two, you will get 56 plus 28. 84. That is MBZ value of parent. What about in case of alkane? 84. In case of alkane, open chain, 86 you got. Right? Last example, 86. So open chain and ring, 2 will be the difference every time. 86 now it is how much? It is 84 or not? Yes. There is a way to identify. 86 means alkane, open chain. If it is 2 difference, 84 means it is ring. Right? Now one more example I will give. See, is it a cycloalkane or not? This is cycloalkane. 70 electron volts I am applying. Then remove one of the electron. You will get radical. And what about this? Cation. Okay? Now, what should I remove? Ethene should be removed here. So go for homolytic fission. This and this forms alkene. Then this carbon, 3-membered ring. So I can write like this, and this is MBZ value. Now apply the same MBZ calculation and give the answer. Here how many carbons are there? Just guess. 5 carbons. First example, today's class, first example, 5 carbons, what is the open chain MBZ value? 72. If it is a ring, remove 2. 70. Just calculate here. That is called DU, degree of unsaturation, ring rule. Everything is remain same. 1, 2, 3, 4, 5. 5 into 12, 60. Every carbon 2 hydrogens. 60 plus 10, 70. Here MBZ value is 70. Now can you calculate below? This one, MBZ value. 42. 36 plus 6. 1, 2, 3. 36, 38, 40, 42. Clear? If I give any functional group, you are in a position to identify what kind of fragmentation is possible. That is fragmentation rules. Any cycloalkane is given, any cycloalkane. In that case, after formation of molecular ion, loss of ethene is a characteristic fragmentation because we are following odd electron rule. According to odd electron rule, if they undergo fragmentation, that will give one even electron and odd electron. fourth rule. Clear? Right. So this is almost all equal. In alkyl, cycloalkane, loss of alkyl as a radical is a characteristic fragmentation. It is a characteristic fragmentation. Means it is the most common fragmentation. Loss of this alkyl in the form of radical is a characteristic fragmentation, which means like this. See, this is a methyl cyclohexane. Now if I apply 70 electron volts, this point I explained. Way to remove, already explained. Way to remove. So can I remove electron from ring carbon or not? Remove this electron. If I remove this, carbon carry radical and this carry positive charge and go for fission. Then what happens? See, here will get positive and here will get methyl radical. That is the answer. That's it. See, here I given only rings, no substitution. Only ring, 3-membered, 4-membered, 5-membered, 6-membered, etc. Only rings without substitution. But here, ring with substitution. If any ring substitution is present, try to remove that substitution in the form of radical. That is a characteristic fragmentation that will follow the rule. What is the rule is saying? If it is an odd electron ion, it is giving a even electron ion and what is one more? Odd electron. Yes, it is right. Clear? Every time you need to check like that. McLafferty rearrangement, double McLafferty rearrangement, retro Diels-Alder reaction, onium ion fragmentation, hydrogen transfer, double hydrogen transfer, everything is possible if you follow the 3 mass spectral pathways. What are 3 mass spectral pathways? Radical cation will give radical and cation. Radical cation can give radical cation and neutral. Even electron ion always give cation will give cation and neutral. You remember the 3 rules? Mass spectrometry will be in your hands. Any functional group you can attempt. Clear? Right. Take down. Yeah, you can. Clear? So from here onwards it is most important. Functional groups are going to come. Alkenes like that. See, if you take any alkene, in alkenes, beta homolysis or allelic fission. Allelic fission is a characteristic fragmentation. It is a characteristic fragmentation. Alkenes. If any double bond is given, beta homolysis is a characteristic fragmentation. You need to know what is alpha bond and beta bond. Okay. See, this is a hydrocarbon, CH2 and here hydrogen. Here carbon carbon double bond I am writing. Right. Suppose if it is on electronic impact, where you will remove electron? Can I remove electron between pi electron and sigma electron? Pi electron or not? After removing electron, see, this is functional group. This is functional group. Okay. In this functional group, first bond is called what? Alpha bond. And what about next bond? Beta. Okay. So, if you break this bond, so this is called beta homolysis. If I break this one, then what happens? See here what you will get? This is radical. Radical, radical, you will get double bond. And what about CH2? CH2 will get positive charge. And what about hydrogen? It is removed in terms of radical. Is it an odd electron ion? Odd electron ion. Odd electron ion responsible to give odd electron ion even. What is MZ value of this one? (41). Very easy. This is MZ 41. And what about this one? What did you no need to count? See, in this what I removed? Hydrogen. Add this hydrogen here. 41 becomes 42. So here this is 42. In case of alkane, what we are getting every time? 43 or not? You remember like that. 42 for isopropyl. 42 for allyl. What is this? Allyl cation. So if you remove hydrogen from beta position, that is called allyl. Functional group first bond is called alpha. Second bonds are called beta. Remember, just assume that this is a double bond. If this is a double bond, in your mind you need to think like this. This carbon carry how many hydrogens? Here this is CH and this is CH2. If I remove one of the electron, here you will get radical and this is positive. Now what about this bond? This is functional group. This bond is called alpha. What is this? Beta, beta, beta. Then what about this hydrogen? Alpha hydrogen. Alpha, alpha, alpha. This is alpha carbon. Alpha carbon attached hydrogens are alpha carbon attached hydrogens are alpha hydrogens. But bond is beta. Functional group attached first carbon is alpha carbon. First bond is alpha. This is alpha. This is alpha bond. Remember, this is alpha bond. Remaining all bonds are. What is this bond? Beta. This is beta. This is beta. Remember, hydrogens are different, carbons are different, bonds are different. All are not same. Clear? This bond is what? Alpha bond. This bond is what? Beta bond. How many beta hydrogens are present? How many beta hydrogens are present? No beta hydrogen. No beta hydrogen. How many alpha hydrogens are present? 3 alpha hydrogens. How many alpha carbons are present? 1 alpha carbon. This is alpha carbon. Generally, you people think that if this is alpha hydrogen, this is alpha bond. That is wrong. Alpha carbon, alpha hydrogen separated by beta bond. Beta carbon, beta hydrogen separated by gamma bond. Remember, see, if these two are alpha, bond is beta. If carbon hydrogen is beta, bond is gamma. If carbon hydrogen is gamma, bond is delta, like that. Is it clear? Right. So every time where we need to cleave? Here we need to cleave, like this. So this fragment you need to remember, allyl cation. Allyl cation fragment, how much? 41. try to cleave beta bonds every time when alkene is given. So suppose if this is a molecule, how to cleave? This is CH2, here carbon carbon double bond. Go for molecular information and beta fission. Beta fission, also called beta homolysis. See, if I break here, what is this? If I break this bond, alpha homolysis. What will you expect in this case? So can I remove one electron here? This is CH3 CH2 and here this is CH and this is CH2. This is radical cation or not? Now go for after generation, then go for what is the answer? Beta homolysis. Can you write the answer? Beta homolysis. How many beta bonds are present? See, which bond it is? Alpha. This one? Beta. So what is this carbon? Alpha. Suppose carbon hydrogen, what is the bond? This carbon hydrogen, what is that bond? Beta. This carbon carbon, that is also beta. Two different betas are there or not? Here how many different betas? Only one type of different betas. But here two different betas. Suppose in first difference, if I remove carbon as a radical, then what will you expect? This and this forms a double bond and here you will expect a allyl cation, right? Suppose if I break carbon hydrogen bond, then this CH3 as it is, this carbon and this carbon carry double bond and this carry CH2 plus, and what is removed here? H dot is removed. Okay. Now what is embedded value of this one? Embedded value is 41 or not? 36, 4, 40 plus 1, 41. Then what is this? $55 here, 41, you add 14, 55. So two are possible, but this is major. Because which radical is outgoing now? Methyl radical, but here hydrogen radical. It is unstable. So this is a predominated one. This is less predominated. Clear? Next, sixth one. Two fragmentations are possible. So whichever is measured, that intensity is very high. So this intensity is very high, this intensity is very less. But this is also possible. Embedded values you write down. Everywhere if I write plus, you write down definitely embedded value. Right. In cyclohexene and their derivatives, cyclohexene and their derivatives, retro-Diels-Alder reaction is a characteristic fragmentation. Cyclohexene, anywhere if it is given, retro-Diels-Alder is most common. You know Diels-Alder? Diels-Alder. Reverse is retro-Diels-Alder. So wherever cyclohexene and their derivatives are given, remember retro-Diels-Alder is most common. See, this is radical cation. Then multi-center fragmentation. Retro-Diels-Alder is a single step multi-center fragmentation. How many steps? One step only. Within one step we are breaking two centers at a time. Here I am breaking, here also I am breaking. It is not a successive fragmentation. What is the difference between successive and single step? Successive means step by step. First this bond is broken, next this bond. That is called successive. But this is not a successive. It is multi-center single step fragmentation. Retro-Diels-Alder. So I can write like this. See, if I break here and here, here will get one radical, here one radical. So I can say dinophile, and what is this? This radical double bond, and here radical, and this is cation. So what about MZ value here? Ah, 1, 2, 3, 4, 48, 50, 52, 53, 54. So MZ value is 54. Okay. So this is a odd electron ion. It becomes a even electron species, and one more is odd electron. Yes, it is possible. Matching or not? Everywhere, if cyclohexene is given, your answer is this one. Now, can you apply this? See. Give the retro-Diels-Alder product of this one. This is 70 electron volts. What is the answer? $70 electron volts. So can I remove radical cation in this one or not? Then where you will break fragmentation? Can I break here? So here you will expect a olefin, then you will get double bond, and this is radical cation. So can I write radical cation like this? Outside I can write radical cation. MZ value. What is MZ value? How much? Here this is already 54. Add 14 to this one. 68. No need to count every time. You try to remember one reference molecule. Based on that you can write. Can you give the retro-Diels-Alder for this? Retro-Diels-Alder. Direct answer. How to write? So this is olefin and this is molecular ion. MZ value 54 for this. No need to generate every time molecular ion, because without molecular ion they never undergo fragmentation. Clear? First is molecular ion, later on fragmentation. Right or not? This molecule lose one electron. This will lose one electron, form this. This also lose one electron, forms one intermediate. That is called molecular ion. Molecular ion always undergo retro-Diels-Alder reaction. So what is retro-Diels-Alder product? Diene and dienophile. How many molecules I am participating? Single molecule or not? So I can say it is a single step multi-center fragmentation. Single step multi-center fragmentation. Retro-Diels-Alder is single step multi-center fragmentation. This step is important. Single step multi-center. Suppose if these two molecules are given in your exam, they will ask like that. How would you distinguish these two in mass spectrometry? They will ask like that. How would you distinguish these two? By using mass spectrometry. Which peaks are helpful to identify these two? 54, 68. Retro-Diels-Alder. They won't ask retro-Diels-Alder directly. By watching this molecule, you came to know that, okay, this molecule will undergo retro-Diels-Alder to distinguish the two molecules. This molecule get distinguished by retro-Diels-Alder fragment. Dienophile value is 54 and here 68. Diene. Additionally one CS3. So will you give this example? See, if this molecule involved in retro-Diels-Alder, so where you will generate molecular ion? Non-bonding or pi? Non-bonding. This is pi, this is non-bonding or not? Non-bonding preferred over pi. So I can remove one of the electron from this oxygen. If oxygen loses one electron, you will get radical cation and this one, right? Then can apply retro-Diels-Alder? Retro-Diels-Alder. Can you give the answer? Now break this one. See, break this and break this. This radical, double bond. This radical, double bond. And what about here? This one. Dienophile and this is diene. And this radical cation as this. Is it odd electron? Odd electron. And what is this? Odd electron and neutral, even electron. Possible? Here how many centers I am cleaving? At a time. Only 2 centers I am cleaving at a time. But here how many centers I am cleaving? 3 centers. That is also retro-Diels-Alder. Is it diene or not? And what is this? Dienophile. But in this case we are generating molecular ion by removing electron from pi. From pi bond we removed one electron. But here we removed one electron from non-bonding. That is the difference. MZ value you need to calculate. Every oxygen assume as carbon, count 12. Then every oxygen add 4. Then at last you add hydrogens. That is the process to calculate MZ value. If this molecule is given, it undergo retro disorder, RDA. Clear? Embedded value how much? See, you need to assume like this: 1, 2, 3, 4, 48. Carbon, just assume as carbon. 48 plus 4, 52. 53, 54, 56. Right or not? See, in this one, 54 or not? This is 54. Carbon replaced by oxygen. If you replace carbon with oxygen, how much values differ? 2. Because 2 hydrogens will be added here. Carbon, 2 hydrogens. But here, 2 hydrogens are removed. And 1 oxygen is added. Okay, MZ value is how much? 56. So when I say the fragment, if I say the MZ value, you are in a position to write the fragment. This is hydrogen and a double bond, a lone pair of electron, 70 electron volts. Can I remove from nitrogen? You will get a radical cation. Then go for fragmentation, multi-center. Can I break here? Break this, three step, and here carbon nitrogen double bond, and here also this, here hydrogen radical cation, and what is this double bond? What is implicit value? You need to, right now you need to remember MZ values. 15 means CS3 plus, 29 means C2H5 plus, 43 means isopropyl, 41 means allyl, 42 means allyl cation radical. Okay, now 54, you remember, 54 is most important, die in radical cation. 54, 56. Clear? Then what about this MZ value? See, every time when carbon, nitrogen, oxygen is present, just assume that all are carbons. Then count with 12. Carbon, 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 carbon. 4 into 12, 48. Right? Then at a time, every nitrogen 2, every oxygen 4. 48 plus 2, 50, 51, 52, 53, 55. What about last case? 54. This is exactly middle or not? M by Z value. Is it 55 or 56? So first one, suppose if these all are carbons, what is the value? 48 or 56, 54? 54. If these all are carbons, 54. If it is nitrogen, 55. If it is oxygen, 56. See, 54, 55, 56. That is a code to remember. You remember this one. This is a radical cation. How much implicit value? Just now I said that 54. Just count here. 1, 2, 3, 4. 4 into 12, 48. 50, 52, 53, 54. One nitrogen is there, 55. One oxygen is there, 56. 54, best number. 5 less than 1, 4. 54. That remember for RDA. Retro Diels order, most important implicit value is 54. If nitrogen is there, 55. Oxygen is there, 56. You remember 54, 55, 56. Clear? So this molecule also undergo retro Diels order. How it is possible? Give the answer. So non-bonding electron we lose this. So here you write radical cation, then go for retro Diels order reaction. So break this. So if I break this, I will get double bond here. This is carbon, double bond O, and this is triple bond. This is radical cation. So this bond all will be broken. This radical, this radical, this radical, this radical forms this one. This is carbon. So these all molecules will involve in this. So this you write down and leave it. So these all are involved in retro Diels order. So after writing this example, are involved in retro-Diels-Alder reaction after generation of molecular ion. If this molecule appeared in anywhere in your exam, first you write down retro-Diels-Alder only. So what is the common thing you observed in these all examples? 6-membered ring. 6-membered, 6-membered, 6C. Everywhere 6-membered only. So that's why cyclohexene, I given that point. Cyclohexene actively involved in retro-Diels-Alder reaction. Clear? This all will undergo retro-Diels-Alder reaction. So here if I want to do retro-Diels-Alder, where should I cleave? This one. So pi bond, remove one electron, you will get radical cation, cleave right side. You will get diene and dienophile every time. Diene dienophile is a common substitutions in this reaction. Okay, next. That is RDA. Right. In alkanes, triple bond, beta homolysis is a characteristic fragmentation. Beta homolysis characteristic for triple bond. Even triple bond also beta homolysis is common. How to write triple bond? Here carbon hydrogen and I am writing carbon carbon triple bond. If I apply 70 electron volts, can I remove one hydrogen? Here carbon hydrogen, here radical cation and here one hydrogen is present. Right? Now go for beta homolysis. This is alpha beta. Beta homolysis. So break this bond. Then this radical forms CH2 carbon carbon double bond and this is CH2 and this is plus and this is hydrogen radical. Similar? What is MZ value? 36 plus 4, 40. In case of allyl radical, 41. 3 carbons, 41, 42, 43. You remember like that. Suppose if I give this molecule, how to write? Mass spectral fragmentation. 70 electron volts, give the mass spectral fragmentation of this one. You try to remember characteristic fragmentation. Alkane, loss of CH2. Branched alkane, loss of bulk group. Cycloalkane, loss of alkene. Alkyl cycloalkane, loss of alkyl. olefin, beta homolysis, cycloalkene, retrodeals order, triple bond, beta homolysis. This point is important. Beta homolysis. Will you write this? Same, similar to double bond, same asterisks are given. So after formation of molecular ion, you will get methyl radical. This is CH2 carbon double bond, and this is CH2 plus. Can I break between carbon hydrogen or carbon carbon? Carbon carbon. Two possibilities are expected or not? Between carbon hydrogen, one more is between carbon carbon. Right. In haloalkanes, alcohols, ethers and amines. Ethers and amines. Alpha homolysis. Alpha homolysis and sorry, it is alpha hydrolysis. Alpha hydrolysis and beta homolysis are characteristic fragmentations. Okay. If any halogen derivative is given, haloalkane, halogen attaches to alkane, saturated. If any alcohol is given, if any ether is there, if any amine is there, these four functional groups, remember, two breakages are most common. What are they? Alpha hydrolysis, beta homolysis. Suppose one example I will give as a halogen C. This is CH2 and here one more CH2. Here I am writing radical cation. Suppose if I do 70 electron volts energy to apply, then what happens? Radical cation or not? What is this bond? What is X here? Halogen. So what is this bond? What does that bond indicates? Alpha bond or beta? This bond here. This is functional group or not? Halogen. Halogen is a functional group. Halogen first bond is what? Alpha. What is this bond? Beta. Carbon hydrogen bond is, that is also beta. See, halogen attached to first bond is, halogen attaches to this carbon. This carbon carry two hydrogens. So I can say this bond is alpha bond. Then this bond is beta, beta, beta. Okay. Then what I am doing now first? Alpha hydrolysis. Alpha hydrolysis means what is the charge here? Positive or not? Can write like this: CH3, CH2, CH2 plus. And how halogen is removed? Halogen is removed in terms of radical. Halogen is removed in terms of radical. Carbon bearing which charge? Positive. Is it alpha hydrolysis? Is it radical cation? Radical cation, radical cation. Possible? Now next one. See. One more, beta homolysis. Where should I break beta homolysis? Can I break here? I can break here, or I can also break this side also. But always try to remove carbon as a better fragment as compared to hydrogen. Suppose if I break here, then what will you get? You will get radical or not? This radical forms double bond. So I can write CH2, and here X with positive charge, lone pair, and what is removed? CH3, CH2 is removed as a fragment in the form of radical. Right? So you can break hydrogen, you can break carbon. Two possibilities are expected, but rule is remain same. Suppose if I break this side, this radical, double bond. Suppose if I break this side, this radical, double bond. On that time, in place of hydrogen, you can write a hydrocarbon chain. Clear? These two names you need to remember. Alpha hydrolysis, then beta homolysis. Okay? I will ask every time these points here. These points are very, very important for these two. This is alpha and this is beta. Suppose if I take alcohol, is it possible, right? See, I am taking this alcohol. This is CH3CH2. This is CH2OH, alcohol. So if I apply 70 electron volts, is it possible to generate a radical cation or not? This is radical cation like this. Now, what are the two fragmentations? What are the two fragmentations? Alpha hydrolysis. What is one more? Beta homolysis. How to write alpha hydrolysis? Same way. Same way, alpha hydrolysis. Then what will get? Alpha hydrolysis. CH3. Can you give the answer? CH2, and what is this? Plus. And what is the byproduct? Hydroxy radical or not? Here how many electrons are present between carbon, oxygen? 2. Add this electron over here. Then this become cation, this become radical. If you add this electron here, this radical is as it is, hydroxy radical. Suppose if it is homolysis, if I break this bond here, homolysis, second step, this radical forms positive charge, double bond OH, and this is plus, and this is removed in terms of radical. Same way, when halogen heteroatoms are present, oxygen, ether, alcohol, and even amines, 2 points are common, alpha heterolysis, beta homolysis. Only thing is, what is alpha bond, what is beta bond, if you identify clearly, that fission points are very easy. Clear? Will you give example for ether? This is CH3, CH2, and here O, CH2, CH3. So I am going to write radical cation. Then write down alpha hydrolysis reaction. Alpha hydrolysis. Alpha hydrolysis. Initially, how many lone pairs are present? 2 lone pairs. 1 electron, here 1 lone pair, here 1 more lone pair. 2 lone pairs are present. If I remove 1 electron, you will get radical cation. Directly I am giving molecular ion. Okay? Then apply this operation. Alpha hydrolysis in ether. Because ether, alcohol, halogens and amines follow alpha hydrolysis, beta homolysis. Whether that fragmentation possible or not. How can you confirm? See, whatever I written, whether it is exist or not, how to confirm? Whether that fission is right or wrong, how to confirm? Follow the mass spectral pathways. Is it odd electron or even? Odd electron. Odd electron will give radical cation, even. Cation, radical. Like that. How to write alpha hydrolysis? See, here shared pair of electron is present, that will be transferred on oxygen. Then what about this carbon? This carbon carries CH2 plus, and what about this? CH3, CH2, oxygen carry. Lone pair, one non-bonding electron. Radical cation. Possible? Possible or not? Suppose same molecular ion I am writing. This is radical cation, CH2 and here one more CH3. Now what I am saying is go for beta homolysis. Where you will do? What is this bond? Alpha. What is this bond? Beta. Beta homolysis. Clue exactly from middle. Then this radical forms double bond or not? Here oxygen, carbon. Here you will get positive charge, here lone pair, and this is CH3 removed in terms of radical. That's it. Is it correct or wrong? Right? Follow the rule. So while you are learning mass spectrometry, many doubts will be created in your mind. Only thing you need to remember is whether it is following the rule or not. Pathway. Odd electron rule, even electron rule. It is odd electron, gives one radical and cation. That's it. So you know amines. Suppose if I write CH3 NH2, is it a primary amine or secondary amine? Primary amine. Around nitrogen, only one hydrocarbon present, primary. 2 is present, secondary. 3 is present, tertiary. Primary amine. Now what I am saying is, in this one go for alpha hydrolysis. First initially one lone pair is present. During electronic impact, one electron is removed, then you will get this one. Then what is this bond? This is alpha. So transfer this electron here. Then what you will get? This is CH3 CH2, here cation. And what about nitrogen? Nitrogen carry here one lone pair and one non-bonding electron. Now it is a cation, it is radical. Radical cation to radical and cation. Yes, it is possible. If you know this one, base peaks identification is very easy for individual functional groups. That is the use of generating radical cation first. You need to know where we are generating radical cation. Right? So can you go for beta homolysis for this? This is CH2 and here I am writing NH2, lone pair. Now beta homolysis. Then where you will write? Can I break this one? If I break this radical forms double bond or not? CH2 carbon nitrogen double bond, and this is plus, and this is CH3. This is important fragment. Many times in CSR examination, this molecule is given. Most of the amines base peak is this one. I'm not writing MBZ values. Every time we write down MBZ value separately. Right now time is not there. So after completion of this class, while you are revising at your home, just write down MBZ values. Practice slowly, you will get. Carbon 12, nitrogen 14. Okay, so this is next one. If I take any haloarenes, in haloarenes, alpha hydrolysis is a characteristic fragmentation. Alpha hydrolysis is characteristic fragmentation. Haloarenes. Can you give an example of haloarene? Haloarene. What is the meaning of haloarene? Chlorobenzene, bromobenzene. This is X. X is nothing but fluorine, chlorine, bromine, iodine. So most commonly fluorine is less preferred. But I am writing, but it is less preferred. So here how many lone pairs are present? 3. If I apply 70 electron volts, then what happens? Here you will get radical cation, right? Now what about this bond? Alpha bond. So that bond I would like to remove in the form of hydrolysis, alpha hydrolysis. So break and add electron here. Then benzene becomes phenyl cation. Halogen become radical. Lone pair, lone pair, lone pair, radical. Radical cation. It is a radical cation. So what is MBZ value of benzene? 78 is pure benzene radical cation. One hydrogen is removed, 77. MBZ value is 77. So when you get 77, one more fragment will possible. If I remove this one, see, if I remove this fragment after getting 77, you will get cyclobutene cation, and one neutral is removed out. See, it is an even electron. Even electron, odd electron. When even electron undergo fragmentation, you will get even electron and even electron. Cation, neutral. What is MBZ value of this one? 51. Wherever you are getting 77, remember, adjacent definitely you will get 51. So 77, 51 indicates that skeleton carry benzene. This is a code to identify. How to identify benzene? How to identify benzene in mass spectrometry? You will get 77, one more is 51 MBZ value. When you get 77, 51, definitely that is belongs to benzene. Molecule carry benzene. So I can take chlorine here, bromine here, iodine. Every time remove chlorine, remove bromine, remove iodine. Then you will get 77, 51. You need to know which is alpha bond and which is beta bond. Be careful. You know what is heterolysis, what is homolysis clearly. If you know the 2 points, where you will clue, what about mass spectral pathways, concept is clear. See, in alkyl benzene, beta homolysis or benzylic cleavage. Beta homolysis or benzylic cleavage is a characteristic fragmentation. Beta homolysis is a characteristic fragmentation. Characteristic fragmentation. If any alkyl benzene is given, can you give an example for alkyl benzene? Toluene. Best example is toluene. Remember, when toluene is given, this is CH3. Now, when I go for 70 electron volts, there is a generation of radical cation, and this is hydrocarbon. Hydrocarbon part is present outside, right? Now what is this bond? This is functional group. Benzene is a functional group. This bond is alpha. Then what about this one? Beta. It is also called benzylic bond. So this bond I am breaking now. This is called benzylic cleavage, also called beta homolysis. Suppose this carbon carry hydrogen, methyl. Break methyl side. If they carry ethyl, break ethyl side, like that. So this radical forms a double bond or not? There is a double bond formation takes place, plus, and here see there is H dot, right? So what about this fragment? See, this fragment is removed in terms of H dot and cation, radical cation. It is an odd electron. Then what happens? See, this bond will migrate here. So after migration of this, you will get CH2 plus or not. What is this? Benzyl. Okay. So this is called benzyl cation. Benzyl cation MBZ value, remember, it is always 91. Okay. So this point I will explain later. Remember, benzyl get converted to tropylium. This is called scrambling. I will explain this point later. Scrambling. Rupture of CC bond. This CC bond will be ruptured here and this carbon will be expanded. Benzyl can be converted to tropylium. See MBZ value. Every benzyl get converted to tropylium, it becomes a 91. Both are same. Conversion of benzyl to tropylium is called scrambling. I will explain later, but temporarily just remember the word scrambling. Scrambling nothing but this one. Rupture of CC bond to give ring expansion product. So this carbon ruptured between these two and slowly expanded. That is called scrambling. Benzyl on scrambling gives what? Tropylium. This is given in DL exam. Statement question. In mass spectrometry, scrambling of benzene cation gives tropylium. Okay. So after getting this C, is it even electron or odd electron? Even. Now remove this double bond into triple bond. Then how many membered? 1, 2, 3, 4, 5 or not? Can I write 5 membered ring? Okay. Then what is removed here? Triple bond. What is MBZ value here? Is it 65? 65 or not? Is it even electron? Even electron to even electron neutral. Possible? Yes. Then see, this is one more even electron. It is giving a fragmentation here now. So one more time, what you will get? Cyclopropanol cation and one more triple bond. That is the answer. So what about MZ value? MZ value is 39. So whenever if you get 91, 91, 65, 39, this is common. When you get 91, 65, 31, remember definitely it is a benzyl. There is a code to identify. Okay, suppose one example I will give. This is one benzyl cation. This is CH2, CH3 they will give. 70 electron volts they will give, and they will give a fragmentation modes here. See, suppose if it is hydrogen, CH3 or not, what is MZ value of this molecular end? MZ value of this molecular end? 92. See, this is 91 or not? Then why you are hesitating? I removed one hydrogen, 92. Right or not? Then what about this one? See, MZ value of molecular ion is 92. Then what about this? What is MZ value of this molecule after formation of molecular ion? You are not catching the points fastly. That MSc theoretical concepts will be dumped in your mind. You are not holding the logics. After completion of these concepts, choose the correct answers I am going to give. Choose the correct answers. If you understand the mass fragmentation pathways, fragmentation rules, concepts, nitrogen rules, then only you can attempt the questions. Otherwise, impossible to attempt. Advantage for mass spectrometry is some basics you can realize very easily. Some concepts also explain stabilities of cation, especially mass spectrometry. See, this carbon carry how many hydrogens? This carbon, 3. This is the difference. This carbon carry 2 hydrogens. If I remove this CH3, if I remove this hydrogen, what is MZ value? 91 or not? If hydrogen is there, 92. So to this 92, if I add 14, you will get that one. There is a logic you need to remember. Clear? I am showing how to remember MZ values. 92 plus 14. I think it is the biggest question. Right? Remember 105, 106. These two numbers are very, very important. 105, 106. In mass spectrometry, some numbers are there. 41, 42, 43, 54, 56, 29, 53. Okay. Then one more is 105, 109, 106. These all are very, very important crucial numbers. So 92 plus 14, how much you will get? 106. Okay. So they will give peaks like this. If this molecule undergo fragmentation, they won't give this molecule. Okay, they will give A. A on fragmentation give MZ value will be 106. They may also give 105. They may also give 91. Then also give 65, 39. What is the structure of this molecule? Like this they will ask. This they will give A. This A on mass fragmentation give this data. Based on this data, you need to confirm the structure. See this. 91, 65, 39 means what? Benzyl. Okay or not? It is benzyl converted to tropylium. Benzyl converted to tropylium. Means first you write down this one. So this is this 92. 91, 105. What is the difference? Otherwise, 91, 106. What is the difference? Methyl group or not? Add methyl to that CH2. Add methyl to CH2. Will you get this one? Yes. You will get 106. 106, 105. What is the difference? 1. Remove hydrogen. 105. All fragments are over. That is the specialty of mass spectrometry. If any unknown cation is given or unknown molecular ion is given or unknown sample is given, based on the mass data, one can identify the structure of this molecule. So what is the code? Code is 91, 65, 39. This number, some numbers you need to remember, no other alternative. While writing mass fragmentations regularly in your class or else in your house, after practicing, some fragment MZ values will be there in your mind. If you know that numbers, by watching the concept, automatically you can attempt the answer very easily. You won't take much more time. Clear? Try to remember 91, 65, 39, 77, 51, 54, 55, 56. Where we learn this? 54, 55, 56. Retro Diels order. Remember that 54. 54 for all carbons, 55 for nitrogen, 56 for oxygen, like that. So for alkene, what is the characteristic fragmentation? Alkene, beta homolysis. Triple bond, beta homolysis. Cycloalkene, retro Diels order. Alkane, loss of CH2, successive loss of CH2. Branched alkane, loss of large branch in the form of radical. Cycloalkane, what is the characteristic? What is the meaning of characteristic fragmentation? Most important fragmentation will produce by following mass spectral pathways. That you remember. Clear? Triple bond, what is the characteristic fragmentation? Beta homolysis. Halogens, alpha hydrolysis, beta homolysis. Alcohols, same. Ethers, same. Amines, same. All functional groups you are learning. See, slowly we are entering into functional groups. Haloarenes, alpha hydrolysis. Benzyl cleavage most commonly for alkyl benzene. If anywhere methyl benzene, ethyl benzene, isopropyl benzene, tertiary butyl benzene, anywhere if it is given. So what is the common fission? Beta homolysis. So that is few characteristic fragmentations of some selective functional groups. So in your next class you will see what are the some other functional groups such as aldehyde, ketone ester, nitrile, nitro, etc. Most commonly you will get what is MECLA40. Okay, so next go for double MECLA40, own ion fragmentation. Okay, so indirect MECLA40, these all are going to come. So next class is most important, don't miss that one. So these all mass fragmentation rules you need to remember. So once if I enter into any functional group, you are in a position to say what is the most important fragmentation with respect to that functional group. Clear? So we'll stop here. We continue our next class.